Okay, well, thanks, Chris, for that introduction, and thank you all for sticking around for the last talk of the day. So I'm going to talk about groundwater vulnerability to nitrate in the California coastal aquifer system and talk about scale dependence of those controls. Oops. Okay, so just want to thank my co-authors here. The talk today is from a paper that was just published in Journal of Hydrology Regional Studies. This paper is part of a much larger project on the water energy food nexus of the entire Asia Pacific Ring of Fire that's funded through the Research Institute for Humanity and Nature. This paper is up online. There's about 25 papers that are part of this special issue on the water energy food nexus, and certainly groundwater contamination is an important consideration within this water energy food nexus. But I'll save the nexus for another talk for another day. But the groundwater vulnerability, I'm probably singing to the choir here, but I want to go over the conceptual framework first. That first of all, non-point source contamination is probably the greatest threat to overall groundwater quality worldwide. It's not that point sources aren't important, but the focus here on vulnerability assessments is usually non-point source contamination. It's important to realize that all groundwater resources and all parts of an aquifer are vulnerable to non-point source contamination, and the physical environment provides some degree of protection from these contaminants. So a definition of vulnerability that I use, there's many definitions out there. The one that I like to use is a few years old now from the NRC, but it's the likelihood for contaminant to reach a specific position, and that's really important for these studies. We're going to focus on a specific part, vertical component of the aquifer after those contaminants have been introduced, usually at land surface at the uppermost aquifer. So this definition, this framework really implies a relative and uncertain nature to groundwater vulnerability, that some parts and some aquifers are more or less vulnerable than other parts of an aquifer. And we're always dealing with uncertainty. We can't measure, monitor aqueous geochemistry, water quality at every single point in an aquifer. So we're always using models to make predictions. So we have to become accustomed to this uncertainty. And so with these vulnerability assessments, the main objective usually is to understand the controls and then make predictions of the non-point source contamination. So there's a whole range of modeling approaches. We've heard a few from Tom just a minute ago, but you can generally categorize them into these three categories: overlay and index, very popular type of vulnerability assessment, very easy to use. It's really more of an initial screening technique. There's a lot of cons with these. They require a lot of professional judgment. They're more subjective. Drastic is a good example of an overlay and index method. On the right-hand side, we have the more scientifically defensible, robust types of models, like process-based numerical models. ModFlow, think ModFlow. These are all based on field data for model calibration and validation. The con is usually it takes a lot of time and money, and there's still a considerable uncertainty when you're using ModFlow for contaminant transport predictions. So myself and a lot of people, Tom mentioned NAQUA, uses empirically based or statistical methods. In the middle, there's a lot of benefits from both overlay and index and process-based techniques, as I'll talk about. And there's some limitations, which I'll get to at the end of the talk. But the main one that's used a lot is logistic regression. I'll talk about that today. So a previous study, just to set the stage here, I've used logistic regression in some national scale and principal aquifer scale vulnerability models, again for non-point source nitrate contamination. The objective here was to evaluate the source, transport, and attenuation factors. So the physical processes that control non-point source nitrate contamination. And we evaluated how these factors vary across the U.S., how they're controlled by different hydrogeologic settings, different climate. And so some of the major findings from this national effort, an important point that I want to drive home today is that the models and maps are highly sensitive to the scale that they're developed at. So the real important point, if you're a local water manager, is to be developing and using models at the same scale that water management and decisions and policy decisions are made at. For example, the national scale model does not work well in Florida, or the Florida model does not work well in the Central Valley. So it's really important to be building these models at the scale that management is done at. One of the other important findings, dissolved oxygen, one of the most important explanatory variables, understanding the redox condition. It's been surprising looking through data sets and talking with managers. Often in groundwater quality monitoring strategies, dissolved oxygen is not measured. So it really needs to be, along with nitrate and a whole suite of other constituents. We found very good models in the Central Valley and the Basin range aquifers, but our California coastal basin model was very poor. So that was part of the impetus for focusing on the California coastal system. So really the objectives here, we're using a similar approach that we did in the previous national scale effort to really understand the source, transport, and attenuation factors, but really to evaluate how these factors are dependent on scale. And I'm going to talk about that in a second. And we're focusing again on recently recharged groundwater. This is the most vulnerable part of an aquifer system. Just to show you some example data here, this is from the High Plains Aquifer. You're looking at nitrate concentration as N, and this is depth of the well screen below the water table. And most of the elevated nitrate tends to be right at the water table, and where there's high capacity irrigation wells, that can cause vertical mixing and drawing down the nitrate to deeper depths. But we're focusing again on the recently recharged groundwater. So here's a study area of the California coastal system. There's over 100 basins, distinct basins. Many of them have been prioritized as high and medium in sigma. They tend to be unconsolidated. We're focusing just on the unconfined or the uppermost aquifer in these often layered systems. If you're not from California, there's a very strong north-south climate gradient here, and land practices vary as well, north to south. The color isn't coming through over here, but what's unique about the California coastal system, there is a lot of agriculture, but unlike, say, the Central Valley, a much larger percentage is used for public drinking. About 46% of groundwater is used for public supply. So understanding the controls on nitrate has a relatively greater implication for drinking water quality and human health. So the statistical methods that I use here are multivariate logistic regression. It's very similar to a linear regression, except that it predicts the probability of the response variable above a threshold. And the threshold that we're using here is a relative background concentration of nitrate of 2 milligrams per liter as N. And what we do when we develop these models, we regress GIS-based explanatory variables within a 500-meter circular buffer to nitrate at the wells. And I won't go through all the statistics, but there's a whole systematic approach to selecting the most statistically significant model and the explanatory variables in those models. The explanatory variables, even though this is a statistical model, a lot of them represent, again, physical processes. So there's over 78 factors that we tested. These are all publicly available. 25 source factors. These represent nitrate loading to the system. So things like farm fertilizer application, land use, atmospheric nitrate we tested. 38 transport factors. These represent nitrate mobilization in the soil, beta zone, and the groundwater. So these are things like depth to water, recharge rates. And also attenuation factors that we tested. These represent denitrification or dilution of nitrate, so things like well depth, dissolved oxygen, redox conditions, which are very important. The well selection criteria, again, these are all publicly available data. They all came from the USGS NWIS database. Our main selection criteria here was tritium. We wanted to, again, select wells that primarily have groundwater that's been recharged over the last 60 years. The wells, again, are screened in the uppermost aquifer. We're using the groundwater quality, the most recently sampled groundwater quality sample, because many of these wells have temporal variability. And we did some filtering in GIS to create a more uniform spatial distribution and also to try to reduce spatial autocorrelation in our models. We have 135 wells, and the groundwater quality sample dates from 1992 to 2010. So the goal here then, we created 4 models, one for the entire California coastal system, and then 3 sub-regional models. So we have a north model, central, and a south model. We had 45 wells within each sub-region, so 2/3 were randomly selected for model calibration, so 30, and then 15 were for model validation. And again, what we're really interested here is the scale dependency of these factors. So how we're defining that in this study is scale dependence if one of these STA factors is significant in either the regional or sub-regional model. That would be scale dependence of a factor, and scale invariance or scale independence would be if the factor is significant in both the regional model and the sub-regional model. So those scale invariant factors are those controls on nitrate that we need to be thinking about at all scales, from local, potentially all the way up to national scale. So here's some results. First of all, the nitrate concentrations from the data from our wells. What you're looking at here are the maximum and median concentrations of nitrate. This again is reported as N. So we have the maximum nitrate was 40, so 4 times our drinking water standard. Our median concentrations varied as low as 0.3 in the north to as high as over 3 milligrams per liter in the central. So these median concentrations are really right around the 2 milligram per liter threshold, so that's very good for this type of statistical model. You want about half of your data above and below that threshold. So the results from the logistic regression models, I'm going to not show all the gory statistical diagnostics and the p-values and things like that, but what the take-home message is, we found much higher statistically significance in our models and very good model fit, better than we had in the national scale effort. And so what you're looking at here are the best 3 sub-regional models and our regional model. And I've listed the explanatory variables from having the most significance in the model to the least, and then STA, again, source transport attenuation. And what you can notice right off the bat is these models all have different explanatory variables in them. So using, for example, the regional model in the north, you're not going to have very good model predictions by doing that. So you really want to focus on whatever region your basin is in and think about those variables that are most important at that particular scale. But what we do see is dissolved oxygen is important in all the models, even the regional model, farm fertilizer. We see soil thickness and other soil properties. This is low infiltration, soil group D, and other land uses like crops that were significant in our models. So I want to go back to the scale dependence idea and look at that a little bit more. So what you have here are the sub-regional models, our regional model, and this is the results from the national scale model I presented at the beginning. Across the top here are the factors that are scale invariant. So these are important, significant at multiple scales. And so again, the most important one here is dissolved oxygen. Again, it's really important to understand the redox conditions in the groundwater. I'll talk about that more in a second. We really want to better understand how much fertilizer is being applied to these systems. It's an important variable at all scales. Soil thickness, important at sub-regional and regional scales. Some of the scale-dependent variables would be things like land use, and that makes intuitive sense that we know land use practices vary, certainly across the U.S., and they vary somewhat north to south across California. Certain soil properties tend to be significant at only some scales, so as well as depth to water and crops. So I want to focus just a little bit more on dissolved oxygen and really the importance of DO. Again, I'm always surprised that DO is not available with a lot of water quality data sets, and it's really an important water quality constituent when you're thinking about monitoring programs for groundwater quality. Denitrification, of course, is this, it's a redox pathway that reduces nitrate to dinitrogen gas, needs an organic carbon as the electron donor, but then the electron acceptor in oxic groundwater, of course, is oxygen. When the system becomes suboxic or anoxic, the next electron acceptor is nitrate. So it's really important in understanding the dissolved oxygen concentrations in your groundwater to understand the onset of denitrification. And if you go through the literature, DO as low as 0.2 to as high as 2 milligrams per liter. There's the beginning of denitrification. Pete McMahon and Frank Chappell in their redox framework, they use 0.5 milligrams per liter DO to indicate really robust denitrification. So some of these numbers we're going to be using in just a second when we make our vulnerability maps. But again, just to think about the importance of monitoring, DO is very easy, cheap to measure when you're developing groundwater quality sampling networks. So the vulnerability maps, we took those statistical models, we used map algebra and GIS to make spatial predictions then of our models. And again, most of the variables are GIS based, so it's easy to make these types of maps. But the problem is DO is not spatially continuous, so we make some decisions here to make maps like this. I've got two maps. The one on the left shows where DO is 2 milligrams per liter for the entire system here. So this would be indicative of oxic redox conditions. Our median DO is right around 2.4, so 2 is right around our median of the data. So this map on the left, A, would indicate if the actual dissolved oxygen in the groundwater limits denitrification and enhances vulnerability of the system. The map B on the right, I use DO of 0.5 milligrams per liter, so this would be more anoxic groundwater conditions. It's about the 25th percentile of our DO data in this study. So again, this would be if the actual groundwater had DO that enhances denitrification and limits the vulnerability. So if you're familiar with California, probably some of these hot spots aren't a big surprise. Salinas Valley, Pajaro Valley, Napa, a lot of the agricultural areas have red, orange and red. This is the higher predicted probability of nitrate exceeding 2. I should mention green is the lowest predicted probability of the nitrate exceeding 2 milligrams per liter. But I think the take-home point here, a really interesting point, is if you look at the difference between maps A and B, you can really see the sensitivity to these types of maps and models to the actual dissolved oxygen concentration that you're using in these. So again, I think more evidence, more support that local efforts really need to be thinking about the redox conditions of their groundwater. These models we validated, so we compared the predicted vulnerability to observed nitrate concentrations using a classification scheme at 3 different predicted probabilities. And so what we see, the percent correct, for example, is very good in the north, very good prediction as well in the south. We have moderate predictive ability in the central and the overall regional models. So these are some regions, the central especially, we can improve upon some of these models and predictions. We had some fairly sparse data here in parts of the Salinas and the central coast where I think there could be some more work done. So to conclude here, any sort of model, any sort of groundwater vulnerability assessment, we always want to think about the appropriate uses and the limitations. And this is no exception here, but I think a lot of what we're all talking about in this conference has really important implications for how we manage nitrogen and other policy decisions within the water, energy, food nexus. And these types of vulnerability maps and models help us prioritize what parts of our aquifer where we need additional monitoring, where best management practices are really needed. But we have to keep in mind these limitations. So the vulnerability models do not show actual groundwater contamination. That's important to realize from a management perspective. These are predictions. The maps I showed here, if you're a local water person and you're squinting to see your local basin, I would caution you just to remember that these are designed for regional and sub-regional analysis. And that said, I think understanding of the important source, transport, and attenuation factors can help with some local scale decisions. But really the best models are going to be the ones that are built, again, at those local scales. I mentioned uncertainty at the beginning of the talk. I didn't do it here in this California study, but I've looked at air propagation and prediction uncertainty with these types of vulnerability models in the past. This is an example from the High Plains Aquifer I've done a few years ago. So, sorry, the color's really washed out, but here is a vulnerability model. The green areas are low predicted probability, red, high to nitrate. And using a Latin hypercube sampling approach, it's very similar to Monte Carlo, we can track air propagation and create confidence interval maps. So on the right, in the areas in green, these are areas that we have the most confidence in our models. Areas in yellow and orange, these are areas where we have the greatest uncertainty, the least confidence. And these orange areas and yellow areas, these are areas where we need to have more monitoring efforts, more monitoring wells, and maybe other best management practices. And this is something I would like to apply here maybe in the California coastal system in the future. Something that was talked, another limitation, something that was mentioned quite a bit on Monday during the nitrate session. The vulnerability models that I showed do not explicitly account for storage and flux of nitrate in the vadosone. In many of the aquifers in the west and the semi-arid, arid west, there are very large reservoirs of nitrate that are moving down at variable rates. And when we think about the future quality of our aquifers, it's really important to have a good handle on how much nitrate we have moving down through these very thick vadosones in some parts of California. So this is just an example of a vadosone monitoring network I've been involved with for many years now. It was started originally as part of the USGS NAQUA program in the High Plains Aquifer, and over the last several years I've installed 8 more sites in Nebraska. We're getting very detailed information about how much nitrate is there, how fast it is, recharge rates under different land uses. And it's really been beneficial for a lot of the land management there in central Nebraska. And I just want to point out, too, that these types of networks are not only for research application. You know, there's lots of maybe journal articles that might come out of this, but these 8 sites were funded at a tune of over $1.5 million from the state of Nebraska over several years, working with one of their water agencies. So they have a lot of, there's a lot of local benefit, and there's pots of money out there if people are interested in expanding this type of network. I would love to talk to you if you're interested in expanding and bringing some of this technology to California. And with that, I think I'm out of time. But I'm happy if there's any time for questions, or my email's up there if not. So thank you.
I don't hear a loud roar from outside, so I think we're okay for some questions.
Thanks, Jason, for the talk. I was wondering, are you suggesting to measure the dissolved oxygen concentrations directly in the field using a sensor, because it may change over time? And maybe a second one, you may also have from the other components like iron, and also say something about the redox conditions of the sample. Comment on that?
Yeah. So yeah, I think the dissolved oxygen should be measured when the water quality sample is taken and when the nitrate is measured. Generally, in these deeper aquifers, I wouldn't expect large wholesale changes in the redox conditions over time. I don't think it's as dynamic as maybe some of the systems you work with in the Netherlands. But yeah, I would definitely measure nitrate, DO, and the whole suite of the redox indicators when you're there in the field. And second part? That's okay. Yeah, okay.
You didn't tell where the oxygen measurements for your model were taken, because my experience is that very often oxygen measurements are very poor, because they're really easy to make, but they're just as easy to pollute because there's this huge impact from the atmosphere. So therefore, I often see that if you go below 1 milligram per liter, there's a great risk that the sample is contaminated. Do you think that can have any effect on what you saw?
Sure. There's all kinds of considerations when you're measuring for DO. I mean, one of the big ones, if you're sampling, a domestic well, oftentimes the water supply is after the pressure tank. So the water's been sitting in the line, and that DO value is not indicative of the aquifer at all. If you're doing a groundwater quality sample and the tube to your groundwater, your submersible well, is exposed to the atmosphere and it heats up, you can be degassing the water sample. So there's a lot of this data came from the USGS, so they take great care in making sure their DO and other water quality parameters are indicative of the aquifer. So yeah, you need to be careful. If you're sampling from a well, a public supply well that has a long screen, you're sampling groundwater over a much larger vertical distance, so that might have a different effect than if you have a monitoring well that has a very short screen and you're at a very low flow rate. So all those things, I think, all are needed. Those understandings of how to collect a proper water quality sample goes into the reliability of your data and your redox conditions.
So just a couple quick questions. I just want to confirm that I understand this correctly. You were looking at young groundwaters based upon tritium age dating, not tritium data.
Yeah, so that the main selection criteria was tritium, so we did want to focus on the wells that had some component that had been recharged within the last 50 or 60 years.
And then what did you use for your fertilizer data?
So a lot of that, the fertilizer data, the land use cover data, the fertilizer data I think was from Barb Ruddy's work. She's at the USGS. I can send you the exact reference. The land use I think we got from the NLCD, the National Land Cover Data Set. Oh. I can send you I don't know the details I can't on the spot remember Barb's work, but yeah. Chris can probably answer better than I can.
Jason, interesting to see the variability in the dissolved oxygen levels and redox conditions in dataset. My question is, do you see that variation also if you look on the different depths? Because I assume all your wells are across different depths in the analysis. Did you try to separate them like up to certain depth and then bit more deeper and bit more deeper, and do you see any gradient in dissolved oxygen? Because it's interesting to see in some case deeper water is reduced or low in dissolved oxygen, and not probably case here, but in our systems a lot of water flows quite horizontally over the top of the shallow water, which still is oxidized and takes nitrate.
Yeah, that's a good point. We didn't actually look at that, so we didn't compare screen depth to DO or redox conditions, but I know generally you would expect to become more anoxic the deeper you go in a groundwater system. I know Pete McMahon and some others have looked at that, vertical gradients and redox conditions, and in general, in many systems in the U.S., it gets more anoxic the deeper in the aquifer that you go. Yeah.
Thanks a lot. And thanks to all the speakers.